Okay, so in that last lesson, we talked about determining whether or not a photo emission could occur because of the threshold frequency of the work function and the photons getting hit in the metal and stuff. But now, once we got a photo emission coming through, okay, we're just going to deal with the maximum. Remember, some of these electrons that are deeper might still pop out if there's enough energy, right, in those photons. Yeah, sorry, in those photons if there's enough energy. But we're just dealing with the ones at the very top. We're going to talk about the maximum kinetic energy, right? The maximum speed electrons being popped up because they use the least amount of energy to pop out. Okay, so how do we measure this kinetic energy? So how do we figure out how fast these electrons are actually moving so I can figure out what the kinetic energy is? And then I can use that information to help me find out what's the work function? What is that minimum energy required to get these electrons out? Okay, we're just dealing, again, we're going to deal with the maximum ones. I'll show you a simulation here in 2 seconds. Okay, so this is the best simulator I can find regarding this idea that not all the photoelectrons are going to be emitted at the same speed. You can see that in this little simulation here, I changed the intensity of light to be like pretty low, so not all tons of electrons coming out. But you notice that some of the electrons are going faster than others. There's a pretty slow one that just popped out there, and then you got some really fast ones coming out. The fast ones are the ones that are just right on the edge of the surface. They get hit by the photon, and the majority of the energy is used as kinetic energy, and only a little bit was used to dig it out. So that was the threshold amount. Some of the other ones that are a little bit slower, you can see that one that's kind of just drifting really slowly across, is most likely that he was deeper back. So when the photon hit him, when the photon came along and hit him, it took him a little bit more energy to get him out. So he wasn't quite at the threshold, right? But he still had enough energy from that one photon to get out. And then he just used whatever is left over to get, because they're all getting the same energy. All these electrons are getting the same amount of energy. Some are using more energy to get out than others. But we're just worried about the threshold ones, the ones that give us the maximum amount of energy because they're right at the surface. They're using the least amount of energy to get out of the metal. So the majority of the energy is now used as kinetic energy, and they go pretty fast. Okay? So those are the ones we're going to deal with here. So how do we measure that kinetic energy? Well, what we can do, like in the simulation here, is I can change the voltage here on these plates. So you can see right now in the bottom corner, there's current. So this 6.83 milliamps of current. I think that's a milliamp or a nanoamp or something. Okay? So I can change this voltage here. You can see as I change it one way, the electron's going to be attracted that way, but I'm not going to do that. I'm going to flip it the other way. And by flipping it the other way, you can see that my current stops. And the reason it stops is because they're being attracted back. They're being pushed back from the negative plate that now I put on the right side here. And the current has stopped. So this voltage that I have here has stopped the current. So we call that the stopping voltage. It stops an electrons from reaching the other side. You can have a zero current now. So I get rid of that stopping voltage. My current goes back up because electrons make it to the other side. Okay? So if I had a little bit more precision on this voltage here, I should be able to get them to just get to the other side, just before the other side, and stop. Maybe I can change this frequency here. There's a way to change this frequency. Oh, I want to go down backwards. Is that enough? Okay, so you can see here, I have a little bit of current now, not as quite as it was before. You can see we're at zero, at 6.83 nanoamps. The current is dependent on the frequency, or is it not the frequency, the intensity of light. So I have only a 10% intensity. So if I increase that, I should be able to increase the current. Yeah, so now I doubled my intensity, I doubled my current. Okay, because more electrons will be coming out. So maybe I'll put that back to 20% there, okay. So you can see they're going across. Now I put my stop voltage on there, my current goes down. It's not down to zero because some are still getting across. So some still have enough kinetic energy to get across, but some, the ones that were deeper down that used more energy to get out, don't have enough energy to get across. You can see some of these electrons get pretty close and just skim the surface. Some of them are going wild and off the side, but you can see some of them get really close, but they don't quite get there, right? But I still have some that actually make it across. So technically my stopping voltage would be like 0.2 in this one. Okay, so let's imagine I had a lower wavelength, so a higher frequency light. Here I've got a current of 2, right? So I can change this voltage until my current stops, right about there. You see some of these electrons are getting pretty close to the other side, but they get pushed back. They never actually get there. So I've stopped my electrons from moving. So I've stopped the fastest of the fast electrons there from getting across. So here I've just backed up a little bit, so I have a little current. Not all electrons are making it across, but some actually make it to the other side. So this would be the stopping voltage here. Okay? So we can use the voltage here and the current to determine, have I stopped the fastest electron? And then I can use that to calculate energy as well. So let's figure that out. So we have a formula based on this already from the previous, or from 2 chapters ago, that said that voltage between the parallel plates is equal to the change of the energy of whatever particle is moving across there divided by the charge of that particle. So I can find out how much energy is changing by, as long as it's just getting to the surface. So it goes from one edge here, gets ejected out really fast, slows down. If it just gets right to the edge, but doesn't quite get there, but then bounces right back, this should be the total change of energy based on the total voltage, because it went the whole distance. So it changed the whole voltage, and then it just went backwards. So I'm just worried about that one wave trip though. So if I did that right to the end, my final voltage or my final speed should be 0. I'm going to make that assumption here, right at the very end. So that means my final kinetic energy is also 0. So I'm just going to change this up here to say final minus initial, and then my final 0. So this is just going to be my initial over Q. I'm going to ignore the negative because remember, if I change my potential, I've increased, or sorry, I lose my potential, I increase my kinetic, or if I lose my kinetic, I increase my potential. So it really doesn't matter which one we're doing. I'm just worried about speed anyway, so it doesn't really matter about the sign. So this initial speed, energy here is its initial kinetic energy if this is going to be a final kinetic energy down here. So this is going to be my initial kinetic energy. And because we're talking about the electrons that get the fastest ones that go right there and just kind of stop and then go back, this is also the maximum kinetic energy these electrons could have. So that's very key, is the maximum ones. It's equal to delta V. Now this voltage that we have here, this very specific voltage, is stopping them. So we have the final velocity be 0. So it's stopping these electrons from hitting this plate and just allowing them to come back. So we also call this V, this delta V, the stopping voltage. It stops it from hitting it, right? Stops the photoelectrons from reaching the other plate. Okay, so VF is equal to 0. Okay, but it has to be the whole distance too. So if I just rearrange this ever so slightly, I can say that V stop, you put the delta there if you want, but you notice on the formula sheet there's not there. V stop times Q is equal to EK max. So I'm just going to rearrange it times the Q up to the other side. Because this is always about electrons, there's a little QE here on the formula sheet. You'll see it on there too. There's a little subscript E there for electron. So this is always about electrons. Electron charge. Stopping voltage in the EK max. Now, we can always just say, now this is my EK max. I can find out what my max speed is by going 1/2 mv squared. That's how I find out how fast they're going if I needed to. Or in this case, we just wanted to measure what is the kinetic energy of these electrons by the certain frequency of light. Okay? Now, other things about this is that there's a conservation of energy going on here. So these electrons, they have energy. We can calculate how much energy these maximum electrons have because we just stopped the voltage. If we just stop the voltage, that means we're just stopping the fastest ones. We got the maximum kinetic energy there, right? We know the energy of the photons that are coming in, right? We know the energy of the photons coming in. We can use that information to calculate the work function of the metal, right? I just wanted to make sure. Yeah, okay, so I'm going to go up here. So we can use a conservation of energy. So I'm going to write that down here. Using conservation of energy, I can say that the energy in, this is my input energy, so this is the photon that comes in. So the energy of the photon has to be equal to the output. And the output here is the kinetic energy of the electron plus how much energy it used to get out. So those two things add together is my output. Okay? So the photon energy comes in, it gets absorbed, it disappears. The photon doesn't reflect away and part of the energy is gone. The photon completely gets absorbed in. So that's got to go somewhere. So some of it goes into the electron to get it out, if it's enough to get out. Only some of it is used there, and then whatever's left over is now kinetic energy and it flies off. Okay? So there's a conservation of energy coming here. So energy in from the photon and energy of the electron out. So this is all electron stuff here. Oops, I don't know why I dotted that. Okay. Anyway, so this voltage that we were talking about before, the voltage that stops the current from happening, stops the electron from reaching the other side, is just called the stopping voltage. If you want to put that little formula there, we can. I just want to look at the formula sheet here. So V stop is equal to EK max divided by EQ. Okay, so this stopping voltage is then used to determine the maximum kinetic energy because it's the voltage that stops the current. You know that when I just had a little bit of voltage on there, I didn't stop the current, I was stopping the slower electrons and not the fast ones. But if I get my stopping voltage to actually stop the current, I'm stopping the fastest electrons, the ones that use the minimum amount of energy, my threshold energy to get out, because now the majority of it was kinetic energy. Okay? Now, we can't determine the kinetic energy of all the electrons because not all of them are ejected at the same speed, like I was saying before, and the demonstration showed that some are slower than others because some are deeper than others, but we're worried about just the threshold ones in this situation. Okay, so we're going to stop the video there, and the next video we'll use some of this information to calculate the maximum kinetic energies of a bunch of different metals here. And yeah. See you in the next video. Bye.